this session we are going to discuss about the flow measurements, the different types of flow measuring devices, what we use for different purposes. See, the most easiest way to measure the liquid flow is by direct method. We have a pipe and we have a tap which is maybe fitted at the end of this pipe. So we'll collect some liquid and we will measure the time for this specific collection of volume, and simply we will divide that collected volume by the time multiplied by density, so we'll get the liquid flow. In case of gas, it is difficult to get this mass flow rate accurately because of the density, right? Because the density of the gas is pretty low. However, the volume flow rate of this gas can be more or less accurately measured in direct method by collecting the gas over this inverted bell jar and therefrom dividing the volume by the respective time over which that volume is collected. So these are the very crude way of getting this volume flow rate measurement. But in process industry, particularly you see that where we have a control room placed far away from that actual site, where some pipeline is delivering the reactant to that reactor or any other process device, and you have to measure that flow because you want to control it properly, control that device properly. So there, the type of the flow meters what we use are totally different from these typical direct flow measurements techniques. So these flow meters, there is a class, and all the flow meters are definitely the flow indicator, but may not be a transmitter. Here, what does it mean? The flow indicator means there is a panel or a scale which may be analog, and it's not giving you an electronic reading, but from certain scale you have to get that measurement, or from certain device reading like manometer you have to get that measurement. So flow indicator means only locally the volume flow rate is being indicated in terms of some inbuilt scale. Whereas transmitter means that you are converting that some signal, some analog this signal in terms of this pressure drop or in terms of some rotational speed. You are generating an electronic signal, and that you amplify and send it to the control room, which may be far away from that actual site. So flow indicator and flow indicator transmitter, definitely there exists restricted scope of the signal transmission for certain devices. Like we'll discuss later that Orifice Meter and Venturi Meter, they can function as flow indicator and transmitter if properly this arranged, right? Whereas rotameter cannot function commonly as flow indicator and transmitter. There will be no transmission facility unless we have a sophisticated optical scheme to record that present position of the float and further transmit it in the form of volume flow rate signal. So rotameters generally are flow indicators but not transmitters. Additionally, we have some other devices like Ketostatic Tube for local velocity measurement which can also transmit this signal electronically. And for large scale open channel flows we use these rectangular weirs and notches, right? Where also we can have certain transmission facility if properly designed. So here we will not talk about the transmission facility in general, but we will discuss the basic operating principles of these flow measuring devices. So what we are going to discuss here, in the flow measurement. See, first we will have overall this broad discussion on restriction flow meters, and in that we are going to discuss about Orifice Meter and Venturi Meter. Right? Next we have area flow meters, and there are many like target meter, we can have rotameter, we can have this target meter, turbine meter, etc. So here we are going to discuss this rotameter one. Next, local velocity measurement devices. Local velocity measurement. Where we are going to discuss this pitot tube. Here the spelling is pitot, but it's pronounced as pitot. Pitot tube and open flow measurement. Here we will have rectangular and triangular wears and notches. Right? That's the overall scope. Here we are discussing pitot tube, here rectangular and triangular, here Orifice and Venturi. So that more or less overall covered this GATE syllabus for flow measurement, whatever we have in this specific subject of fluid mechanics. There will be some extension of that idea when we go for flow instrumentation in process control and instrumentation, right? So here, let's start with this restriction flow meter. You see that in restriction flow meter, it's typically used for internal flow, where we artificially create a restriction and obstacle the flow, right, by creating this sort of reduction in available cross-sectional area. So as a consequence, what will happen? This is centrally placed, more or less it is centrally placed like this. Let's say this is the center line. So what will happen? Here you see the diameter is here D1. However, as the fluid has to move through this right hand side, it has to pass through this narrow opening, right? But this is not the lowest cross-sectional area of the flow. Here we will have inevitable boundaryless separation at this point. So here we will have a boundaryless separation, and further the fluid will continue to reduce its cross-sectional area up to a certain point, and after that they will again expand and occupy the whole cross-sectional area. So this region where the cross-section of that fluid attains this minimum area, this region we call Vena Contractor. So this is the Vena Contractor, and that will be our point 2 for our analysis, and here definitely we will have the wake region, right? So let's say the velocity here is V2. There will be some assumptions we will be listing that, and far upstream from this restriction let the point be 1, right? Here also we will list that we are considering the velocity to be uniform. Let's say it is V1. So what are the assumptions for this analysis? The assumptions, if we list, the first one is a steady flow, second incompressible flow, third uniform velocities at section 1 and 2, fourth no curvature of streamlines, that is pressure at cross section, pressure at section 1 and 2 are uniform, no frictional loss, and Z1 is equal to Z. So steady flow, incompressible flow, uniform velocities at section 1 and 2. Definitely it is a questionable assumption because here the velocity is for any real life flow, the velocity will not be uniform, there will be a profile. Here also we will have a profile, right? So no curvature of streamline, that is the pressure at the section 1 and 2 are uniform, right? But they are different definitely, and no friction loss, and the datum at Z1 and Z2 it's perfectly horizontal. For the time being we are considering that. So if I apply continuity between point 1 and point 2, the pipe continuity equation that typically which is the outcome of this V dot dA, it's equal to 0. So obviously it will be minus of V1 A1 plus V2 A2 is equal to 0. So you can get that V2 bar is equal to V1 bar A1 by A2. Next we apply the Bernoulli equation between point 1 and 2. So this Bernoulli equation gives P1 by rho, this 7 will be, this alpha 1 is equal to alpha and close to 1, let's say. So P1 by rho plus alpha 1 V1 bar square by 2 is equal to P2 by rho alpha 2 V2 bar square by 2. So we are considering this turbulent flow. And you see that whenever the velocity here, as this area is reduced, the velocity will increase, so P2 will decrease. So if I measure the pressure here and the pressure here, let's say this is P1 and here it is P2. So from the difference of P1 and P2 we can relate it, or we can actually calculate the volume flow. So how we can do that? So this alpha 1 is 1, alpha 2 is 1. So P1 minus P2 divided by rho is equal to V2 square by 2 minus V1 square by 2. So V2 bar square by 2, 1 minus this V1 bar square divided by V2 bar square, and that's equal to V2 bar square divided by 2, 1 minus this A2 by A1 whole square, right? So V2 bar is equal to 1 by under root 1 minus A2 by A1 whole square into 2 delta P divided by rho, where this pressure drop delta P is P1 minus P2. Correct? So if this velocity, if we multiply it by density and the respective area, definitely we will get the theoretical estimate of the mass flow rate. Like m dot theoretical will be V2 bar whatever we have calculated into A2 into rho. So this is A2 divided by this 1 minus A2 by A1 whole square into 2 delta P into rho. Right? That is the theoretical mass flow. But actually you see, we have to think about certain issues. This is definitely a questionable assumption. Uniform velocity is at section 1 and 2. Definitely it will not be perfectly correct. That no friction loss. And additionally the streamline, it will have a curvature and there will be some certain variation of this pressure. But the most questionable assumption is a uniform velocity at section 1 and 2. Additionally, if I have to measure the flow, I have to get A2, right? I have to get the value of A2 and this. So A2 is not a geometric dimension of that system, it's rather a dimension associated to this hydrodynamic profile of that system. So question naturally arises how to evaluate A2. We can't do it because the system is closed and we have no visual access to this specific location or the region, right? So as a consequence, what we do, that we will further put a correction, or not correction, we will further write that okay, A2, which is the Vena Contractor area, is close to this throat area. This area is, let's say, 80, right? So replace A2 by area of the throat, that is 80. Okay? At the same time, to mitigate the different questionable these assumptions and replacement of A2 by AT, we have to put a correction factor, right? So this we will write that AT into CD divided by 1 minus beta to the power 4, I will explain what it is, into root 2 delta B into rho, where beta is basically dt by d1, right? dt by d1. CD is a correction factor called the discharge coefficient, and this 1 minus under root of 1 minus beta to the power 4, this is a technical term, it has got a technical name, it's called velocity of approach factor. This is called velocity of approach factor. So this is my final working equation. So you have to note that CD is to be evaluated from experiment, and that is basically the very well known calibration experiment. That means that once we have an orifice meter, I don't know the value of CD, so but I know what mass flow rate is flowing because it is calibration experiment, everything is known. And we know the area of the throat, beta, we will measure the pressure drop, and what we will do, I will plot this m dot versus the entire expression of this right hand side excluding the CD. So I will get some plot like this, a point like this. So over the region, if I fit a straight line, I can calculate from the slope the value of CD, because here we are plotting this m dot, and in this direction we are plotting this A2 divided by 1 minus beta to the power 4 into 2 delta P into rho. So it must be giving you a straight line, and from the slope we can determine the value of CD, and this is typically called a calibration experiment. However, as you go on changing the mass flow rate, the CD also changes, right? So CD here, the inference is that CD is a function of upstream Reynolds number here. And what is the nature of the functionality? It is C infinity plus A divided by B into A divided by, right, RE d1 to the power n. So this is the type of relation where C infinity, A and n are system specific constant. But the overall nature of this relation will be just like this. So this is the general description regarding this restriction flow meter. So with that working formula and this variation of this discharge coefficient with pi Reynolds number, let's discuss the specific aspects of orifice and Venturi meters. So you see orifice meter, there is some difference between these two structures. Orifice meter is just a disc with a central orifice, right? In common design, it will be a central orifice, and which is inserted in the pipe segment upon introducing a current, right? So I'll discuss it. So it's a small, compact, handy structure and it's quite flexible. However, Orifice meter has got a problem. What is that? There will be a permanent pressure drop. You see, in the restriction flow meter we have discussed that from point 1, that is far upstream, at Vena Contractor there will be a pressure drop. But once the fluid is again occupying the entire cross section in the far downstream, then the pressure must increase. However, in the far downstream the pressure is not at all equal to the pressure in the upstream. There is a permanent pressure loss, right? P1, and if the far downstream point we consider as 3, then P1 minus P3 is a permanent pressure drop, where P1 minus P2 is a temporary pressure drop, and that we are measuring for flow measurement. So in Orifice meter, what happens? The permanent pressure drop is higher compared to the other restriction flow meter commonly used, and that is Venturi meter. Okay. So as the permanent pressure drop is high, so we can say that Orifice meter, but the construction is simple. So Orifice meter is something, a device which has got very low capital cost but high operating cost, right? Whereas Venturi meter is a large bulky structure. Definitely it requires a lot of material and there are some fine finishing necessary. So its capital cost is high. Whereas in Venturi meter there we have an excellent pressure recovery. That means that P3 will be nearly 98 to 99% of P1. P3 is the far downstream pressure, whereas P1 is the upstream pressure. So P3 is basically close to 99% of P1, and as a consequence we have a very low operating cost, right? So what meter we have to choose, right? That's typically kind of a thumb rule, but we don't solve this problem. It's mostly thumb rule or guess or experience based on which we will fix that whether we are going to use this Orifice meter or Venturi meter. But commonly, if the pipe size is large, then no matter whatever is the capital cost, we must go for Venturi meter. But for small pipe size, we definitely, because in large pipe size the pressure itself is costly, right? As we have to use a large size pump and there will be huge power investment. So for large pipe size, we have to focus, we have to pay specific attention to permanent pressure drop, and that's why Venturi meters are recommended, whereas for small to moderate pipe size, Orifice meter are recommended. So what is the design of Orifice meter? You see, we have this pipe where we introduce a cut, right? We introduce a cut, so this is the pipe. It's a very rough drawing. Now we attach this flat flange on both of the pipes. And here we insert this orifice plate and this is the center line, and generally the plate is beveled outward and we have the gaskets in order to make this entire assembly leak proof, right? So this is the basic design, and we have to bolt it, these two flange, we have to connect it through bolt joint. Here also we have the bolt. Right. So this is the orifice meter, but definitely we have to go for pressure tapping. This is the most common type of pressure tapping. We will discuss it. See, that's the basic structure, and this will be the direction of flow. So, first question, why the orifice meter or the orifice plate is beveled outward? See, if you bevel it inward, what will happen? The Vena Contractor's location will be far downstream, right? Or relatively far from the plate. But if you bevel it outward, the Vena Contractor will be somewhere here, right? So as you are reducing the distance, what will happen? Your head loss here, because of this separation and all, over this, for traversing this much of length, will be minimal. And you want the Vena Contractor to be formed close to that orifice plate, and that's why it should be beveled outward, right? So that's the basic reason that why we go for Vena Contractor diverging out. Next, what are the different pressure tapping? The most popular pressure tapping is called D/2 tapping. If D is the diameter of the pipe, then in the upstream we will install the pressure tap at a distance D from the plate, whereas in the downstream it will be D/2. So different this pressure tapping. What do we have? First one is D/2 type tapping. Second is called flange tapping, where both these are at a distance of nearly 2.5 or 25 millimeter from the plate. So that's called flange tapping, and 3 is the typical corner tapping. So where we have this manometer limbs located here, right? So definitely the most popular one is this D/2 tap, which we commonly use in industry, and you have to note that in terms of this governing equation, as we go on changing the pressure tapping, actually the CD value will be different. Commonly the CD for orifice meter for standard tapping varies from 0.6 to 0.66 for orifice meter, right? Next we will discuss the Venturi meter. You see, the Venturi meter is a large bulky structure, and this structure looks like this. If this is the pipe, here we have the flange. I'm not drawing in detail. The detailed drawing is given in the handout. So here is the flange. Here the Venturi meter. First, it's a constant cross-sectional region, right? Like this. Next, we have a reduction of cross-section. This converging section, upstream converging section. Next we have a throat, and next there is a long diffuser section like this, with a gradual change, very gradual change of cross-sectional area. And what is the utility? I will explain. There is a gradual change of this entire cross-sectional area, and it's like this, right? So this is the throat region. This is the converging upstream section, and long diffuser section, right? Now we put the pressure tap, one at the throat and another here. So these two are pressure tappings, which may be connected to manometer or any other differential pressure transducer, right? So this angle is 5 to 7 degree, whereas this angle is around 20 to 23 degree. Now you see that whenever I am going for 20, 23 degree diverging section, definitely in this region, say let's say this is 0.1, this is 0.2. So as we move from 0.1 to 0.2, you see the flow is in this direction and it is a converging section. So what will happen? Del P del X, if X is this direction, is negative because velocity increases because of divergence, but velocity we don't want too high. So it is a gradual increase of velocity with a gradual reduction of pressure. So the pressure is acting as a additional, because of the convergence, the pressure, additional pressure gradient is acting as a driving force. But here, when it expands from this throat to this far downstream, what will happen? This is a region of adverse pressure gradient, right? Because of diverging, or I should not say it is an adverse pressure gradient, but because of cross-sectional change, because of cross-sectional change, then you will have, this adverse pressure gradient. And there is every possibility that the flow will separate out. And flow separation will lead to what? Flow separation, where in Orifice Meter we have an invariable flow separation. Here in Venturi Meter we want to avoid that flow separation because we want excellent pressure recovery. So flow separation, in order to prevent that, the change of the cross section must be gradual, and that's why the angle is 5 to 7 degree. So as the area is increasing slowly, very very slowly, so the chances of flow separation is getting reduced because we have actually reduced the magnitude of this adverse pressure gradient. So as a consequence, we have an excellent pressure recovery in Venturi Meter, and because of that, the CD in Venturi Meter is 0.98 to 0.99, as high as that for Venturi Meter. Right? So see, we have discussed about the design, the working equation for these restriction flow meters. But what if a Venturi meter is vertical or inclined, whether this working equation will be changing or what will happen? This was a 2007 GET question. That it's very flat question, but unless you know it, it's quite difficult to answer. That if I have, like this is the center line, say this is a Venturi meter, right? And here this is 0.1, and let's say at the throat this is 0.2. So we have fixed manometer like this, right here. So this is the manometer, and that's the manometer reading. So this is the common datum. Here this datum level of the 0.1 is say Z1. Here for 0.2 it is Z2, right? So this gap is delta H. Say this is delta H, and this one is H0. So if I apply Bernoulli, and the flow is in this direction. If I apply Bernoulli between this 0.1 and 0.2, what I will get? P1 divided by rho plus say alpha 1 and alpha 2 is equal to 1. V1 bar square by 2 plus gz1 is equal to P2 by rho plus V2 square by 2 plus gz. Correct? So you can write this P1 divided by rho g minus P2 divided by rho g, P1 by rho g minus P2 by rho g plus Z1 minus Z2 plus Z1 minus Z2 is equal to V2 square by 2 minus V1 square by 2. So basically P1 divided by rho g plus Z1, that is the piezometric head at point 1, minus P2 divided by rho g plus Z2 is equal to this V2 square by 2, 1 minus this V1 by V2, so it will be A2 by A1 whole square. Right? So you see this piezometric head we will writing at H1 star and H2 star. So V2 is going to give you this 1 divided by under root 1 minus A2 by A1 whole square into 2H1 star minus H2 star. Right? Now let's think about the manometer reading. Here the pressure, let's say it's P1, and let's consider this is the surface over which we are balancing the pressure on both sides. So that's P1 plus this side is P1 minus H0, right? Sorry, Z1 minus H0 into rho into G. And that's equal to this P2 plus Z2 minus H0 minus this delta H into rho into G plus this delta H into rho m into G. Delta H into rho m into G. So you see this, if I now group it down, that P1 plus Z1 rho G minus H0 rho G is equal to P2 plus Z2 rho G minus H0 rho G minus delta H rho G, then plus delta H rho m G. So H0 rho G and H0 rho G cancels out with minus sign. So we have that P1 divided by rho G plus Z1 minus P2 divided by rho G plus Z2 is basically equal to delta H into rho m minus rho. Right. Divided by this, divided by this rho G. Divided by this rho G. So, you see this delta H. So, this is H1 star minus H2 star. And we have got the same equation. If I replace it, I will have the same manometer reading 1 minus A2 by A1 whole square into twice into this delta H rho m minus rho divided by rho G. So this is, if we replace in normal horizontal Venturi meter or Orifice meter, if I replace this delta P in terms of manometer reading, right, I will get the same equation, because see, the equation was this V2 is equal to 1 divided by 1 minus A2 by A1 whole square into 2 delta P into rho, 2 delta P divided by rho. And now delta P is equal to what? Delta P is equal to this here, no, G will not be there, G will not be there because G cancels out. So delta P is equal to delta H into rho m minus rho into G. So rho m minus rho into G. So basically we are getting the same equation, and here it is the piezometric head. So basically it is not this we have done a mistake here, calculation mistake, that whenever I am dividing it by rho G, so here it will be V square divided by 2G, right? V square divided by, or I am dividing it by G, so it will be V square divided by 2G. So here also it is V square divided by 2G. So obviously this formula, if it is V square divided by 2G, so here it will be rho G. So finally this V2 by 2G is equal to 1 divided by 1 minus A2 by A1 whole square into this rho m minus rho into delta H divided by rho. The same equation as this. So what is the outcome of this analysis is that the working equation for Venturi meter or Orifice meter, like whatever restriction flow meter we are thinking of, it's remaining same no matter whether it is horizontal, vertical, inclined, everywhere it will be same, provided we replace this delta P manometer, delta P, the pressure drop in terms of manometer reading, that is delta H into rho m minus rho into G, right? So that's all about the restriction flow meter. Next we will go for local velocity measurement. We'll discuss the local velocity measurement using pitot tube. So here this concept of static, dynamic and stagnation pressures are to be noted, and we will revisit again. Static, dynamic and stagnation pressure. See, the static pressure is same as thermodynamic pressure, what we use for thermodynamic calculation. Like how to measure it? If the liquid is flowing through a pipe and you insert a pressure probe which is perpendicular to the pipe, this will give you P, which is the static pressure. Right? Next, dynamic or rather stagnation pressure. If a fluid is decelerated to zero velocity, fluid decelerate to zero velocity, a fluid decelerate to zero velocity, then the pressure of the fluid, is stagnation pressure, right? Like if I think of two different points, here point 1 and here point 2, you have pressure, velocity V and pressure P, which is basically the static pressure, and here the velocity is 0 and P will be P stagnation, ST. And if I apply the Bernoulli's equation between these 2 points, you see we will get that P by rho plus V square by 2 is equal to P stagnation divided by rho. So P stagnation is equal to P plus half rho V square, right? So this is the stagnation pressure. This is the static pressure, and this one is the dynamic pressure. So in pitot tube, what will happen? We will insert a capillary, right, which is horizontal to the direction of flow, and facing the capillary opening will face the flow itself. Just like there are two design of pitot tube, like this is the capillary. Here in the tube we place a capillary like this, and that is to manometer. So what will happen, you see, if here the pressure is P and V, here the fluid, because of the strong interfacial tension effect, will not be able to flow. So it is basically decelerated to zero velocity here, right? So at this capillary mouth we will have the stagnation pressure. So we can measure the stagnation pressure, and if I know the static pressure, we can calculate the local velocity. But knowing static pressure itself is a problem, so we will go for a collective measurement. So this is the normal pitot tube, standard pitot tube, and we can improve the design as Ketostatic tube. What is that? So here this basic pitot tube structure will remain intact, but additionally we have a cover, right? A closed cover. And here we will put an opening. So if I now connect the manometer like this, so in this space we will have stagnation pressure, here we will have static pressure. So this is transmitted to this limb where we have static pressure, and here it is the stagnation pressure. So stagnation pressure is higher than the static pressure, so we will have this sort of manometer reading, right? So this difference, this H, so you see we can write this H into rho m minus rho into G must be equal to half of rho v square. So V we can find out as this 2hg into rho m minus rho divided by rho under root of that. So that gives you the local velocity of the point, and as you go on changing the location of the point, we can actually determine the different velocity, and we can maybe trace the velocity profile in turbulent flow which we have discussed previously. So after this pitot-static tube, next we'll think about another group of these flow meters called Orifice Meter, right? So in Orifice Meter, not Orifice Meter, area meter. Area meter, right? Area meter has got an advantage over this restriction meter. See, in restriction meter, we have volume flow rate, or rather the mass flow rate, proportional to under root of delta V. So this relation is non-linear, right? The variable which you are actually measuring, and from there you are calculating the mass flow rate. So this is the primary variable, this is the target variable. So primary and target variable, they are sharing a non-linear relation. Whereas in area meters, we have a linear relation between m dot and measured value, right? So we'll discuss this typical example of area meter, which is rotameter. It's a tapered tube. Definitely the angle of tapering is rather 2 to 3 degree, right? And here we will connect it to the pipe, and we have a float, right? A metal or plastic float like this. So when there is no flow, the float will be located here. Like the float will be located here. Now as we have a flow, the float has to move up, because increasing flow requires increasing cross-sectional area. Like as the float moves up, as the tube is tapered, so the gap between the float, the annular gap between the float and this tube increases. So it is expected that whenever we are increasing the flow rate, the position of the float will be actually increasing, right? So we have to locate this position of the float to this float. So you see on that float, the force balance on the float, what it will yield? It will yield this mass of the float into G, then mass of the float divided by, under static condition, mass of the float divided by rho float into rho into G is basically equal to drag force. So half of rho into A float into U square into CD. So you see this typical drag formula for static float position. The float is not moving now. So under equilibrium position, this U, the fluid velocity over this annular region, like if I think of this cross section, let's say this is the float. So this annular region, the fluid will flow and it has got a velocity u, right? We consider uniform velocity here. So it is twice into mf into g 1 minus rho by rho f divided by this rho into af into cd under root. Okay. Now this u, the rotameter is designed over the specific volume flow rate range such that the u remains, we will assume that u remains nearly constant over that specific operating range. Like when it will happen, see mfg for a specific fluid rho, then float density rho f, this af, everything is constant. But cd may be dependent on the Reynolds number or velocity. But we know that cd versus re curve for sphere or for any other object will look like this, more or less tentatively. So if I operate this rotameter over this constant cd region, we can actually guarantee that u will be not changing over that specific range of particulate Reynolds number, like from REP1 to REP2. So this is the CD by REP plot we have discussed. So this is the operating range, right? So once we got it and we have justified this u to be constant. Now you see that q will be is equal to pi by 4 tube diameter minus fluid diameter square multiplied by u, and u is constant. So this dt square will be tube diameter will be what? dt square will be float diameter, because here this is same as the diameter of the float, otherwise the float will move down, right? So the inlet tube dia and float dia must be same. So this is df plus here if this is h, see this is h, and this is alpha, then perpendicular is equal to h into tan alpha on both sides. So it is df plus 2 tan alpha whole bracket into h, right? So let's call it df plus a into h, where a is very small, because tan alpha is in the order of 2 to 3 degree. So dt square minus df square, we can approximate, or we can write it as equal to this df square plus 2 df a h plus a square h square minus df square. So this cancels out and we can safely approximate it as 2 df a h, as a square h square is much smaller than 2 df a h. So we can drop this down, right? So as we drop this, my final equation for this rotameter so the final equation becomes q is equal to this pi by 4 into 2 df a h, so that is this part, into u, which is 2 mfg 1 minus, or rather if you multiply this, it will be rho f minus rho divided by rho f into rho into af into c, right? So that's the equation. Now sometimes we may have questions like, we have a rotameter and we are operating it with helium and we have got this much of H, this much of reading, right? Now if we change this gas to say carbon dioxide, what will be the reading? But everything else, nothing else is given, see? Rho f is given. So what you can do, this rho f as it is much higher than rho, so you can approximate this formula as some constant, and as this density is important here, so it is as some constant into under root of rho 1. This rho f we can disregard, okay? Because rho f is much higher than rho, so this rho we can drop, so only we have rho in the denominator, so q will be proportional to k divided by under root of rho, and therefrom we can solve the question. And what I have mentioned, that the area meter have a linear relationship between m dot and measured variable. Now what is the measured variable here? H. So we have Q is proportional to H. So that's about the area meter. We can have the different other area meters like turbine meter, target meter, etc. Now the last topic is the notches and wears. See, these are used for flow measurement in open channel. Just like if I have an orifice meter and truncate it, it becomes a circular, this notch or circular wear. Generally, these are used for notches or metallic structure, small metallic structure which are used for measurement of flow in open drain, whereas wears are large machinery or concrete structure used to determine the flow in canals, rivers, etc. Okay. So you see that we have the basic hydrodynamics in both the cases is same. Wears can be considered as a much scaled up version of the same notch, right? So what are the structures? The structure is simply like this. Either it may be a rectangular notch or a triangular notch, right? And here the approaching liquid will fill up certain height. Let's say this is the height h, right? And the flow rate, we will know that it will be a function of the height here. In triangular notch, this height again h, right? Half of the angle is theta. So here also we will find some different function, say f1h. So in both cases, what we have to assume is that the velocity of approach of this fluid, the surface velocity of the fluid to this wear or notch must be very small, and generally it is the case this relative to the velocity in the downstream side, right? Because there is a restriction and we have a high velocity here. So approach velocity, if it is 0, right, then we have to think about the depth-wise distribution of velocity. Say this is h here and this is dh. So you see this, if I apply Bernoulli's equation between point 1 and point 2, we can actually calculate the velocity here will be under root of 2gh. So why? Because here the velocity is 0, here the velocity is say v. The pressure at point 1 and point 2 are same because it is atmospheric pressure, and there is a change in the datum level which is of height small h. So obviously we get under root of 2gh. Truly Bernoulli's equation cannot be applied because these two are not along a streamline, but tentatively we are doing it. We will manipulate it via correction factor. So once we do it, we will have that dq is equal to v of h into this area, that is b is the width, into dh. So q will be is equal to, rather q theoretical is equal to 0 to h under root of 2gh into b into dh. So you see here under root of 2g, then b, then h to the power 3 by 2 divided by 3 by 2, h to the power half, and this is 3 by 2. So that's the q theoretical. So 2 by 3 under root of 2g into b into h to the power 3 by 2. Correct? So q actual, here we will write some discharge coefficient which are to be determined via calibration into h to the power 3 by 2. So the relation between the flow rate, volume flow rate, and the measured variable is something like this, q proportional to h to the power 3 by 2. Whereas here you see that if this is h, the width is varying. The width here is varying. Now what will be the width? This width here for this location h. So actually the width is the total one, right? So here you see this much is h minus small h. This much is H minus small h. So H minus small h into tan theta is this gap. So twice of H minus small h into tan theta is this. And if I consider again a strip of this thickness dH, so here the velocity, just like previous, will be under root of 2gh. So the flow rate Q will be equal to under root of 2gh into twice of H minus h into twice of H minus h into tan theta into dH. So if I integrate it, root over 2g into 2 into tan theta, right? H into h minus this h into h to the power half rather, and here h to the power 3 by 2 dH, and this is dq basically. So we have to integrate it from 0 to h. So it is 2 under root of 2g tan theta, and here it is h to the power 3 by 2. So limit will give you h to the power 3 by 2 plus h to the power 5 by 2, denominator is 3 by 2, and here h to the power 5 by 2, denominator is 5 by 2. So it is 1 by 3 minus 1 by 5. So from there, so it is this 2 by 3 minus 2 by 5. So how much it will be? 15, 10 minus 3, 6. So it will be 4, 4 by 15, and additionally we have 2. So it is 8 by 15, and this is the theoretical flow rate. So actual flow rate, there will be a discharge coefficient into root 2g tan theta into h to the power 5 by 2. Right? So this is for the triangular notch, and Q here is proportional to h to the power 5 by 2. Now you see that here dq dh is proportional to 5 by 2 into h to the power 3 by 2, whereas here dq dh is proportional to 3 by 2 into h to the power half. Right? So triangular notches are more sensitive, right? Here the sensitivity of Q towards the change in h is much higher. So triangular notches, a triangular notch are relatively accurate than this rectangular notch. Actually here it should not be said as accuracy, or relatively triangular notches are of relatively higher resolution, right? Here we maybe differentiate between, say, some centimeter cube per second of flow, where we cannot do it in this rectangular notch, because there this h to the power half is the respective sensitivity proportionality. Here it is 3 by 2. So rate of change of volume flow rate with respect to h, here it's much higher than this previous case of rectangular notch. But triangular notch, definitely the construction is a bit difficult compared to that of rectangular notch, and this is prone to damage, particularly here, right? This will undergo corrosion because, particularly for metal, if it is a metallic structure, then the sharp edge is more prone or is susceptible to corrosion. So that's all for this volume flow rate measurement and the flow measurement of fluid. So the additional topics like the laser Doppler anemometers, target meter, turbine meter and everything will be discussed in process control and instrumentation, where you will have some more details of these flow measuring devices. But for fluid mechanical standpoint, this much is more than sufficient.